So we're going to do our math using the heating curve as kind of our guide to which equation and which constant to use. So the question itself is going to give us the hints so we know where to look. So like for example, it says how much energy must be absorbed for 5.0 grams of ice, so we know we're on the low side of the chart, the left side, to melt at the freezing point. And notice it's not talking about the ice like changing temperatures or anything like that. It just wants it to melt. So it's just implying it wants the phase change. So what we want is this region right here. Because again, like if it had wanted the lower region, it would be like the ice is at -50 and it's changing to -10. Like it would have a temperature involved, and there's no temperature in this equation. So we just look, in the purple is our formula, and notice that right here is my H value, the H of fusion. So I'm going to use Q equals N times delta H of fusion. Notice that I have the 5.0, which is my mass. Notice that I am solving for energy. Q is heat energy. So I need to change my mass into moles, and then I can use it with the equation. So I'm going to take my 5.0 grams, and this is water. I mean, it's ice, but it's still water. And then the molar mass of water is 18.02 grams, because of oxygen's 16, and there are 1.01 for the hydrogens, but there's 2 of them. And in moles of water. So that right there, my grams will cancel, and that gets me to that mole term. So then that times my fusion, it is 6.022, and then I'm going to write the unit like this so that you can see that the moles are going to cancel, leaving me with an energy unit, which is what I need. So I'll just pull over my calculator. I like to go across the top, so I've got 5.0 times the understood 1 times 6.02. It's 2, not 22. Whoops, 6.02. And then divided by 18.02. So that gives me 1 point, and this has 1, 2 sig fig, so 1.7 kilojoules. I just have to get this shifted on over here. And then the next kind of question is how much energy must be removed, and this is the same amount. It's crystallizing at the freezing point. So it's just wanting it to go the other direction. So it's asking for the quantity of the energy. So the interesting thing is that it actually takes the same amount. Whether you're talking about one direction or the other, it's the same amount. It's just this is what has to be heat added. And then this has to be like heat removed. You know, like by the environment or something like that, pulling the heat out of it. All right, and then let's look at this one. You can also be asked in terms of a different part of the equation. So we're still looking at, let's see, how many grams of water can vaporize? These were left out at the boiling point if 15.0 kilojoules of heat were added. So again, we're not talking about a temperature change. So we're just going to be using our same Q equation. It's this right here because it's at that boiling point. It's still that Q in delta H of 8, but we are using this 43.9. So I'm going to plug in that 43.9. And this one is giving me a kilojoule. So if you're not sure of a number, look at the unit. So that one is kilojoules of heat, 15.0 kilojoules. So to get N by itself, notice that N is moles, but I can always get moles to grams with the molar mass. So that's what I'm going to do. I'll divide both sides by 43.9, 43.9, and then I'll bring this over. 15 divided by 43.9 is going to get me 0.342. That's my moles. So I'm going to go ahead and turn that into grams. Same molar mass of water. So I'm going to take that number half, And then I'm going to do times 18.02. And so that number gives me 6.16 grams of water. So you can use that equation in different ways, solving for what you need to. And this is just another variation just to make the point. How much energy is absorbed, so this is a heating curve, as that much, that's a mass of ice, we're at ice again, changes temperature 50 to 40. So negative 50, negative 40. You'll notice this is the first time we've even seen the delta C in all of this. So we're going through a temperature change. So this is negative 20. So this is going to be like way down here to get to like negative 50 and negative 40. But we're still on that diagonal, which uses this equation right here. So MC delta T, notice that the C we need to use is at 2.09 though, because it's for ice. So Q equals M times C times delta T. Our masses are 3.0 grams, 2.09. That's joules per gram degrees Celsius. That's our C. And our temperature is final minus initial. So the final is 40 minus negative 50. And so that's going to make that a positive. So that's going to give us 10 right there. So it'll be 3 times 2 times 10. And back to 2 sig figs. So it looks like I would be running that to 63. And my unit here, so my grams canceled here. My degrees Celsius is canceled there. They were added together. And so that leaves me with a joule is what my Q is. And it does matter a lot with what you're about to see happening next to keep track of whether you're talking about the energy being a joule or a kilojoule.